In a certain turbo machine, the fluid enters the rotor with an absolute velocity having an axial component of 10 meter per second. So here it is axial component of absolute velocity is 10 meter per second. Thus the tangential component in the direction of rotor's motion is 16 meter per second. The tangential speed of the rotor at the inlet is 33 meter per second. Tangential speed of the rotor, so that is 33 meter per second. At the outlet of the rotor, the tangential speed of the rotor is 8 meter per second. Again, he has given the tangential speed at the exit of the rotor. The absolute velocity of the fluid is 16 meter per second in the axial direction. So at the outlet, the absolute velocity of the fluid is 16 meter and that is axial direction. Evaluate the energy transfer as a work between the fluid and the rotor. So we need to find out the energy transfer that occurs between the fluid and the rotor, and then in this turbo machine, is this turbo machine a power absorbing or power generating? And what is the change in the total pressure if the process is loss free and the fluid is water? So if the fluid is water and the process is loss free, if there are no losses, then we need to find out the change in total pressure. In the previous problem, we had done the similar problem where we had calculated the energy transfer, and then we have seen that it was a power generating device. So here we have to do the same, and then we need to find out the total change in pressure. In the previous case, we had calculated total change in temperature. So these are the things which you have to do in this problem. First, I'll start with listing out the data. So the data given in this problem are, first one, they have given the absolute velocity having an axial component of 10 meter per second. So at the inlet, we have the axial component of absolute velocity. So axial component is Vf, that is the flow velocity at inlet is 10 meter per second. And the tangential component, which is in the direction of rotor, is 16 meter per second. So tangential component at the inlet is Vu1, and that is 16 meter per second. And the tangential speed of the rotor at inlet is 33 meter per second. So the tangential speed of the rotor is capital U, and I'll call it as U1 because at the outlet he has given some other value. So U1 is equal to 33 meter per second. At the outlet of the rotor, the tangential speed of the rotor is 8 meter per second. So at the outlet, it is U2, and U2 is given as 8 meter per second. Now, the absolute velocity of the fluid is 16 meter per second. So V2 is 16 meter per second, and that is in the axial direction. So this is very important. In the previous class, I had told you that if the fluid, the absolute velocity of the fluid is axial or radial, it means to say that the alpha related to that fluid will be 90 degree. So here we are dealing with the outlet, so alpha 2 will be equal to 90 degree. So these are the data given in the problem. With this data, we need to calculate the energy transfer which occurs between the fluids, and then we need to calculate the uh, we need to find out whether it's a power absorbing or power producing or power generating turbo machine, and then we need to find out the total change in pressure, so delta P naught. So these are the two things which you have to calculate and say whether this is a power generating or power absorbing turbo machine. So since U are different for inlet and outlet, so for inlet it is 33 and for outlet it is 8, we cannot write a common velocity triangle in this case. So I'll write a I'll write uh, two different velocity triangles for inlet and outlet. So for inlet, I'll write the same general velocity triangle. So we have the base and then here we have VF. Then I'll draw two lines. So here this is our V1, this is our VR1, and this is BF1, and from here till here it is U1. While writing the outlet velocity triangle, so I'll write U. U is towards right. This is U. This is U2. And then from this end, I have to write V2. So V2 is a vertical line because alpha 2 is 90 degrees. Since alpha 2 is 90 degree, V2 is a vertical line, and I'll join these two ends. So now I have the outlet velocity triangle. Now I'll name the parts. So this is V2 and this is alpha 2. From here till here it is U2, and this is our VR2, and this angle is beta 2. So V2 and VF2 are same. VF2 are same because V2, the angle of V2 is 90 degree. So V2 is a vertical line. So for vertical lines, we don't have any horizontal component. So V2 and VF2 will be same. So now we have constructed the velocity triangles. Now we need to calculate the energy transfer. We know that energy transfer is given by, okay, E is given by U1 VU1 plus or minus U2 VU2. So here VU2 is 0. Because of that, we don't have the second term. The energy is U1 VU1. U1 is 33 multiplied by VU1 is 16 meter per second. So energy transfer will be equal to 33 multiplied by 16 is 528 joule per kg. So this is the enthalpy change that occurs between the inlet and outlet of the turbo machine. And since E is positive, the energy transfer is positive, it's a power producing or power generating turbo machine. Now we need to find out total change in pressure. So to find out total change in pressure, we have the relation delta H naught will be equal to delta P naught divided by rho, where rho is the density of the fluid. Or in other words, I can write delta P naught will be equal to rho into delta H naught. So if I do this, we know that the working fluid is water, so the density of water is 1000 kg per meter cube multiplied by delta H naught is 528 joule per kg. So I'll get 528000 Pascal or Newton per meter square, or I can write it as so 5.28 bar. Okay, in this problem, at a stage of an impulse turbine, the mean blade diameter is 0.75 meters, its rotational speed being 3500 rpm. The absolute velocity of the fluid discharging from the nozzle inclined at 20 degree to the plane of the wheel is 275 meter per second. If the of utilization factor is 0.9 and the relative velocity at the rotor exit is 0.9 times that at the inlet, find the inlet and exit rotor angles. So Also find the power output from the stage for a mass flow rate of 2 kg per second and an axial thrust on the shaft. Now we need to find out the inlet and rotor or the exit rotor angle, so that is beta 1 and beta 2, and we need to find out the power output. If the mass flow rate is 2 kg per second and the axial thrust on the shaft. Okay, I'll list out the data here. The data given in this problem are: first one, they have given the diameter of the mean diameter of the rotor, that is 0.75 meters, and the rotational speed is given as 3500 rpm, and the nozzle is inclined at an angle of 20 degree, that is alpha 1, and the velocity of absolute velocity of the fluid at inlet is 275 meter per second, and the utilization factor epsilon is 0.9. Then the relative velocity at the rotor exit, that is VR2, is 0.9 times of VR1. I'll start with the general velocity triangle which we have drawn for most of the problems. So first I'll write the base, then I'll write Vf1 and Vf2, and then I'll join these to form a general velocity triangle. So here this is V1, this is VR1, this is Vf1, and from here till here it is U, and this is VR2. VR1 and VR2 starts from the same point. This is V2. V1 and V2 starts from the same point, and this is Vf2. So from here till this end it is Vu2, and from this point till the right end it is Vu1. U, we need to calculate U. U is given by pi dn divided by 60, or pi into 0.75 into 3500 divided by 60. So U, when you calculate, U will be equal to 137.44 meters per second. So now we need to calculate V1, V2, VR1 and VR2. So V1 is given and alpha 1 is given. From that we can calculate VU1, VF1 and VR1, because now we know U. So I'll calculate VR1. So first I know that if I take V1, VU1 and VF1 at that right angle triangle, then if I write sine of alpha 1, so that will be equal to Vf1 divided by V1, which implies Vf1 will be equal to V1 sine alpha 1, which will be equal to V1 is 275 into sine alpha 1 is 20. So we'll get Vf1 as 94.06 meter per second. Now I need to calculate Vu1. So Vu1, I'll directly write it as V1 cos alpha 1. I'll substitute the values now. So root of V of 1 is 94.06 square plus VU1 is 258.42 minus U is 137.44 whole square. So when you substitute the values and calculate VR1, we'll get VR1 as 153.24 meter per second. Once we know VR1, now we can calculate beta 1. So we know the inlet velocity triangle values. Now we need to find out the outlet velocity triangle values. I'll take next page here. I'll take a blank page. So now we need to calculate VR2 Now we need to calculate V2. So to calculate V2, what I'll do is I'll utilize the utilization factor. The epsilon is given by V1 square minus V2 square divided by V1 square minus R into V2 square. And if you see the problem, it says that it is an impulse turbine. So in the case of impulse turbine, the degree of reaction R will be equal to 0. So the degree of reaction is 0. So I can write a utilization factor 0.9 will be equal to V1 square minus V2 square divided by V1 square, because R into V2 square will be 0. So now I have only one unknown here. So I can find out V2 square. So, or I'll write it as V2 square will be equal to V1 square minus 0.9 times of V1 square, or I can write 0.1 times of V1 square, or V2 will be equal to V1 into root of 0.1. So when we substitute the value of V1 as 275 into root of 0.1, we get V2 as 86.96 meter per second. Once we know the value of V2, now we need to calculate the value of VU2. So in this velocity triangle, now we need to calculate VR2. So if we know VR2, then we will be able to find out the remaining two values. So we don't know alpha 2. So we need to find out VR2. Once we know VR2, I know beta 2 because it's an impulse turbine. Beta 1 and beta 2 will be same. So I have beta 1 value here. So that will be equal to beta 2. From that, I can find out V of 2, and once I know V of 2, since I know V2, I can find out VU2. So first I need to calculate VR2. So to calculate VR2, I'll just write these three lines, that is V2, VR2 and U in the next page. I'll just write those lines here on that triangle. I have U here. Cosine rule. If you remember cosine rule, if I know angle, one of the angle, then I can, if I know two edges, then or two sides, then I can find out the length of the third side. So according to cosine rule, so if you remember cosine rule, if I know an angle, then I can find out the length of opposite side. So for beta 2, opposite side is V2. So I can write V2 square will be equal to U square plus VR2 square, that is the squares of the two adjacent sides for the angle, minus 2 times of U into VR2 cos beta 2. So this is the cosine rule. So with this cosine rule, what we have to do here is we need to calculate the value of beta 2. Since we are considering the losses, I cannot say beta 1 is equal to beta 2. So I need to calculate the value of beta 2 here. So I know V2, I know U, and I know VR. Now I need to calculate beta 2. So V2 is 86.96 square. That will be equal to 36.82 degree. So this is the value of beta 2. So beta 1 was 37.86. Beta 2 is 36.82 degrees. Once you know the value of beta 2 and beta 1, now we need to calculate the value of VU2. So if you know the value of VU2, we know mass flow rate and we can find out the power. So first, we have solved the first part of the problem where we have asked to find out inlet and exit rotor angles. Now we need to find out the power and axial thrust. So now let us find out VU2. So I will complete this velocity triangle. If I divide the V2 into vertical and horizontal component, then we will get VU1 and VU2 and VF2. So now to find out VU2, I can use the Pythagoras theorem because I know VR2, I know U, and I know VF2. So VF2, okay, I don't know VF2. So here, what I can do is, since I know beta 2, I can write horizontal component of VR2, that is cos of beta 2, that will be cos beta 2 will be equal to adjacent side u plus VU2 divided by the hypotenuse VR2. So I can use this to find out the value of VU2. So if you rearrange this, VU2 will be equal to so here we have a minus, which indicates that whatever the direction we have assumed here is wrong. And if I reconstruct the outlet velocity triangle, it will be in this form. So we have the base, so here this is V2, this is alpha 2, this is VR2. From here till here we have VU2, and that is in the same direction as U, and the entire length will be U. So this is the correct outlet velocity triangle. So whatever the direction we have assumed here is wrong. Now we know this outlet velocity triangle. This is beta 2. Once we know that, now I know the value of VU2. I can find out the power. So power is given by m dot into u into VU1. Since VU1 and VU2 are in the same direction here, I'll write it as minus VU2. Now we need to find out the axial thrust. Sorry, axial thrust FA. FA will be equal to m dot into VF1 minus VF2. Please find out the value of VF1 and VF2 and substitute here. I'll give you the value of FA. The axial thrust value is 22.82 newtons. But I request all of you to find out the value of VF1 and VF2 using the inlet and outlet velocity triangle, and then substitute in this equation to get the axial thrust. So I'll stop the session here. I will continue with problems in the next session.